Alright, so I'm going to try to do my best to give an example of how you might apply Gauss's law. I say my best try because, it's really hard to draw using this software, so I'm doing the best I can. Let's say we have an infinitely long sheet of charge, and with a uniform charge distribution sigma, where sigma is q over a, and that just means that if you have a surface A, there's charge uniformly distributed over it. I did not draw that well, but looking at the sheet from above, it kind of looks like this. You have the same amount of charge everywhere along the sheet. So this is kind of looking at it from above. Obviously, it's not infinitely large, but just pretend that it is. And this is looking at it from the side. So we're going to have an E field, an electric field generated by the charge on this sheet, and it's going to go radially outward from the sheet. It's only going to go up and down. It's not there's not going to be any components going any which way. It's only going up and down, and so we can use that symmetry um, to apply Gauss's law to find the electric field at a point a certain distance away from the sheet of charge. So um, I chose kind of a cylinder. It doesn't really matter what you choose, as long as it's straight, like a rectangular prism or a cylinder. And so we apply Gauss's law. Gauss's law I wrote right here. It says that the closed loop integral of E dot dA is equal to the charge enclosed divided by epsilon 0. And in this case, the charge we're enclosing is sigma times A, where A is the area of our Gaussian surface. So if this is a cylinder, then the area we're talking about is the surface area of a cylinder. So in this case, for reasons of symmetry, the E field is the same um, any given distance away. So right here, if you draw a line, let me draw a line. If you draw a line like right here, everywhere on that line, the E field is going to be the same for reasons of symmetry. And again, I can't really explain symmetry to you. You either see it or you don't. But the electric field due to this plane is going to be the same at this anywhere as long as you're the same distance away, provided that you're not so far away that provided you're not really far away. Let's just leave it at that. So in this case, I chose a cylinder, and like I said, the E field is only going up and down, so I don't have to worry about any E field going through the sides of the cylinder, just through the top and the bottom. And so I have an E field going up here, and an E field going through down here, and so my magnetic flux is going to be 2 times E times A, where A is the area of this end. And the reason it doesn't matter is because there's an A on this side of the equation, and they're going to cancel out. And so our result that we get is that the E field, due to an infinitely long sheet of charge, is equal to sigma divided by 2 epsilon 0. So I don't know how much sense that made. Hopefully it kind of makes sense. This is one of the few examples you can use Gauss's law in for reasons of symmetry. Notice we have symmetry here because, like I said, any distance you go, the E field is going to be at the same strength. So every position on this line, the E field is the same, and the same with this line, and so on and so forth. So hopefully that helps.